Okay, let's talk about simple harmonic motion. So simple harmonic motion, we define it, and this is important, this is a really key definition that you must learn and memorize by heart. It is a motion of a body whose acceleration A is directly proportional to its displacement x from a fixed point, which we call the equilibrium position, and is always in the opposite direction to that displacement. So if you think about a pendulum on a clock, it has an equilibrium position here, and the more you move it to the side, the faster it will try to accelerate back to the center. And you can see that most easily with something like a swing. If you push a younger sibling just a little bit on a swing, and move them a few degrees, you have quite a small force acting back on them. So you have a small force which will give you a small acceleration. But if you push them really, really far and you're really straining to have them out there, well then they have a big force, and that leads to a big acceleration. And we see that with everything. If you have these singing bowls, they oscillate, they vibrate back and forth along their walls. A mass on a spring that oscillates up and down around a central point. A ball rolling back and forth in the bottom of a container. Again, it always oscillates around a center point. And again, the more you move it to the side, the bigger the force is on the ball, and the more it wants to go back, or the faster it accelerates back to its equilibrium position. So with that in mind, this is a really common graph that we see, where we have here the force acting on the object, which, remember, force is equal to mass times acceleration, so the force is proportional to the acceleration. And here we have the displacement from the equilibrium position. So the only correct one here is B, because they are proportional to each other, but most importantly, they are in the opposite direction to displacement. And it's worth just taking a moment just to think back on that. Here's my pendulum. If I've displaced it that way, the force is in the opposite direction. Here, my person on a swing, they have been displaced that way, the force is in the opposite direction. So we can say that the acceleration is always proportional to negative x, and actually we can say that acceleration is equal to minus omega squared x. Now this omega comes from angular velocity is 2 pi over the time period, where, as usual, time period is the time taken for one complete oscillation. I will prove at the end of this video why that is the case. You don't need to know it, but you do need to use it. So it's up to you whether you want to stick around for the derivation. Okay, so some key terms then. Amplitude, that is defined as the maximum displacement from the rest position. So if I have this object undergoing it here, this distance would be amplitude. Period, time taken for one complete oscillation, which you're familiar with. Frequency, number of complete oscillations per unit time. We can also say frequency is 1 over the time period. Angular frequency, that's 2 pi over t. Here, so this angular frequency, this will be in radians per second. And we'll see in a minute why radians are really useful. Phase difference, that's a comparison in radian between two positions within one oscillation. And we'll do more of that in a future lesson. Now, this is a bit that's semi-optional, but it really helps to explain what comes next. And when we think about whenever you look at a course in physics, you'll always see circular motion and simple harmonic motion always taught together. And why is that? Well, on the right-hand side here, I've got an object undergoing a circular motion. And so you can see it's going around with a radius r from a fixed position here. So it will have, for example, an angular velocity which is equal to whatever angle it goes across per unit time, and of course, same thing, well, it will complete 2 pi radians within one full time period. Now there are loads of proofs that you can do, and we will do some of these in our lesson, that show that the movement of something undergoing simple harmonic motion, so this is SHM, simple harmonic motion, this is circular motion, the movement of this up and down is equal to the vertical component of this object. So we'll always see a real similarity between them. Now because of that, that's why we often use omega, angular frequency, angular velocity, for something undergoing simple harmonic motion. Even though it's not actually completing a circle, I can still say it's 2 pi over t. Now again, that won't make sense unless you stick around for the final bit where I go through a derivation. For A level though, you just need to know omega is 2 pi over t, and that, as I said before, acceleration is minus omega squared x. That's acceleration at any point. So you can see therefore acceleration max will be minus omega squared multiplied by amplitude. And we can see that the acceleration when x is 0, that will be 0 because x is 0 there. And you can see that in these graphs. So if you plot a graph of displacement against time, well, a really common question they ask you is, here's a displacement time graph for something undergoing simple harmonic motion. So in other words, it's its x position against time. So you can see this would be bouncing up, bouncing down, bouncing up, bouncing down as time goes along. How do you get velocity? Well, it's just the gradient. Remember, velocity is the gradient of a displacement time graph. So at this point here, I can see my gradient is large and positive, so I get a large positive value on my velocity graph. Here, my gradient is 0, so I get a value of 0 here, and you'll see these match up. So you basically, to get the velocity graph from a displacement time graph, you just get the gradient of it, and it looks like another sinusoidal curve. To go to velocity to acceleration, you just get the gradient again. And you'll see again here, my gradient starts off at 0, so my value is 0 down here. My gradient is large and negative, so I have a large and negative number down here. Now remember, we said acceleration is equal to minus omega squared x. So I can see acceleration is proportional to, but in the opposite direction, to displacement. And here you can see that these two are mirrors of each other. I hope if I could spell mirror. These are mirrors of each other, which is pretty cool. This is just it flipped upside down. Now, in your exam, you may be asked to prove when something is undergoing SHM. This is a really advanced technique. It's at the A and A star level, but it's quite a cool little example of this. So here I have a mass on a spring. Now, if this is equilibrium position, I can say at any position, the force on this spring is equal to spring constant multiplied by the extension, or the movement from equilibrium. But in this case, I'm also going to say F is equal to negative kx. And that's because the force, if I displace it down this way, the force will be up in the opposite direction. So I can write it like that. Now, I also know that force is equal to mass times acceleration. But I've also said that force is equal to minus kx. So my acceleration, therefore, is minus k over m multiplied by x. If I see over here, though, I can say that acceleration is always equal to minus omega squared x. So therefore, this part, this k over m, this must be omega squared. So I can say omega squared is equal to k over m. Omega by itself must be square root of k over m. But I can go even further. I know that the time period of something undergoing simple harmonic motion is 2 pi over omega, because remember, omega is 2 pi over t. So I can say, therefore, that the time period of this object is 2 pi divided by the square root of k over m, which simplifies to 2 pi lots of the square root of m over k. This gives me the time period of a mass on a spring. And you're going to see this equation crop up a lot over this course. You don't actually have to prove how to get it, but knowing how to do it is a really cool thing to be able to prove. Okay, very last thing I want to show you very quickly, because I'm running out of time, is how we actually prove the equation A is equal to minus omega squared x. So, if we're assuming something acting with simple harmonic motion is acting exactly the same as something undergoing a circular motion, but I only care about its displacement in the x direction, so I care about this x component of it, then I can say that its displacement x is equal to r cos theta. Yeah, this is theta, r cos theta. Now I know that theta is omega t, so I can say x is r cos omega t. Now from maths, I know that velocity is the differential of x with respect to time. So I would show some detail, but I'm just going to use the chain rule, and I'm going to say dx by du multiplied by du by dx. I'm going to let u equal omega t, and you can try this at home and figure it out, but what you should get is r omega cos omega t. Actually, I think it's minus r cos omega t. That gives me v. Now acceleration is dv by dt. I'm going to do the same thing again, and that will give me minus r omega squared cos omega t. But remember here, I said x is r cos theta, so that is equal to omega squared multiplied by x. And there's the proof. Now, if you can't sort of stop that, pause it and go through it, remembering this is a chain rule, don't worry, it probably means you haven't learned that in maths yet. But once you have learned it in maths, that's a nice little proof there of why, sorry I forgot my minus sign, of why this isn't just made up, this is mathematically valid and rigorous, which is pretty cool.